Hey, Chemistry 2, AP Chemistry. Let's go ahead with Part B of the atomic structure. Let's discuss electrons and protons. Okay. So, and this is mostly review for most of you guys from last year. In the late 1800s, scientists were passing electricity through glass tubes that contained a very small amount of gas, sort of like oxygen or neon or fluorine. And when the power was turned on, the tube emitted light and glowed. Now, the positive electrode is called the anode, and the negative is called the cathode. They called the rays cathode rays because they appeared to be coming from the negative end of the tube. And most of y'all guys remember this. So, a lot of people speculated what these cathode rays were. Were they waves or were they particles? Because when you placed an object in the path of the rays, there was a shadow of the objects placed in their path. Okay? So we know light waves will cast a shadow, so it could be light, or it could be a stream of tiny particles, which would be stopped by the object, and again casting a shadow. Now, scientists found that they could deflect this beam by subjecting it to an additional electrical field. So, what would the beam deflect toward the deposit? Why would the beam deflect toward the positive plate? And does this indicate the rays are light rays or particles? Let's look and see. Because the beam is a negative, right? It's got a negative charge. And it has to be particles because light waves would not be deflected by an electrical field. So, they also could deflect the beam by putting it in a magnetic field. So, why would the beam deflect toward upward in the magnetic field above? And does this mean they're light rays or particles? Here we go again. Okay. Let's see. Why would it? Oh, because in physics we have the right hand rule, where the magnetic field above a negative charge would deflect up. So they've got to be particles because light waves would not be deflected by a magnetic field. So, scientists determined that a very weak electrical field could deflect the beam a great deal. If the particles are really easy to deflect, they either have a very small what? Or a very large, or both. Well, they would either have to have a very small mass, because it's easier to move something small if you're big, or a very large charge, because opposites would attract. Back too far. So, J.J. Thomson, some of you guys might remember him, and his team were able to determine this charge to mass ratio. And this is what it is. It's 1.76 times 10 to the 11th coulombs of charge. That's a lot of charge per kilogram of mass, or C over kg. Now, at this time, they didn't know what the charge was. They didn't know what the mass was. They just knew that the ratio was pretty large. So either he had a very large charge, a very small mass, or both. Now, what was very interesting was these negatively charged particles were found in all gases that they looked at. Oxygen, fluorine, bromine, anything they experimented on. And they all had the same charge to mass ratio. That's pretty huge. So you might be dealing with the same things. So what these physicists proposed of these negatively charged particles, they wanted to call them electrons. So we did. These particles have the same charge to mass ratio as the negative particles generated by static electricity, heated materials, and illuminated materials. So, what characteristics about the cathode rays led them to believe they were negatively charged? Because they were small. Their behavior in an electrical field. Their behavior in a magnetic field. B and C are, I need a little help. If you recall, what they did in an electric field and what they did in a magnetic field is what they determined, okay, where they hypothesized about the characteristics. And they thought that they were negative. Okay. Now, which of the following indicated that the cathode rays had a very large charge to mass ratio? They caused the fluorescent screen to glow? No. They were easily deflected. They were deflected towards a positive electrode. They were deflected toward a negative electrode. Or, man, I have no idea. How about they were just easily deflected? Okay, so that means they had a big mass, small mass, or something, or a very large charge. So, a guy named Millikan, he squirted oil drops into a box, and then he passed high-energy X-rays at the box, hoping to knock electrons off the air molecules and onto the oil drops. So this is how his device was. He was able to look through that and actually count the drops. Okay, he squeezed some oil through here, and this is a charged device, if you would. All right, so you had a anode and a cathode. Okay, and then he put some ionizing radiation, some X-rays through here. And what he was hoping to do was stop the oil in midair, okay, and knocking off some of those electrons or some of that charge. Now, these are the results we measured. Okay, one drop had 4.8 times 10 to the minus 19th coulombs. The other one had 3.2 times 10 to the minus 19th coulombs. So these are all the same, 6.4 and 9.6. So what he found was that the charges on each of these drops were a multiple of a number. Okay, can you determine what the multiple of the number they're all a multiple of? Let's see. If I divide 3.2 by 2, I get 1.6. Let's use that. So if I divide 1.6 into 4.8, I get 3. That's a multiple of 3. Okay, another drop, 6.4. 1.6 divided into that, I get 3. Okay, fourth drop, 9.6, I get 4. So these are all multiples of 1.6 times 10 to the minus 19th coulombs. Okay, so if the charge of an electron is 1.6 times 10 to the minus 19th coulombs, which is what Millikan determined, and the charge to mass ratio is 1.76 times 10 to the 11th coulombs per kilogram, we can determine the mass of an electron. All right, by dividing 1.76 times 10 to the 11th by 1.6 times 10 to the minus 19th, and we do that. All right, and then divide by itself, we come up with 9.1 times 10 to the minus 31st kilograms. And that's pretty small. If you don't believe me, see. So, which of these could be a charge of a drop on the Millikan oil drop experiment? Well, let's see. It'd have to be C. Because if you take 1.6, divide that into 8, okay, you come into a factor of 4 or 5, whatever it is, times 10 to the minus 19th. All right, so the magnitude of the charge on an electron was determined in the what? Millikan oil drop experiment. So that was pretty huge. All right, so guys, there's 2 parts to the videos, 2 parts to the PowerPoint slides that we were going through. And that'll be enough for y'all to watch. I'll come back and then we'll start talking about the nucleus. Again, most of what we went over was review from last year.